Welcome to Module 3. Today we're going to be looking at covalent compounds. We looked really extensively at ionic compounds in the previous module, and now we're going to look at the second class of chemicals, second of only two, which is covalently bound molecules. And at the end of this module, we're going to look a lot more at water, which is my favorite covalent molecule and maybe yours as well. Water is the universal solvent. It's the solvent of life. We're going to go on about how many unique properties water has, which really are based on the nature of how covalently bonded molecules are formed. So to begin with, we're going to be looking at ionic versus covalent. We want to get a good understanding about how these are two very different classes of chemical interactions that yield very different chemical properties. In our last module, we really focused on ions and ionic compounds. That's one way that we can form collections of atoms made of different elements that make some new compounds, meaning things that are made up of more than one type of element. But now we're going to look at that second class of compounds, which are covalent. And covalent is different because when we looked at ionic compounds, we have one atom that has actually lost electrons and one that has actually gained electrons. And that principle of becoming neutral with negative and positively charged stuff, that's very much ionic. But covalent is very different. This is what forms molecules, and most of the human body is made up of covalent molecules. The water that makes up most of our mass is covalent. Proteins, DNA, virtually all the macromolecules we look at, with some exception, will be much, much more covalent than ionic. And most medications, drugs, this is a really important class of compounds to know. And so, how do drugs bind to receptors? How is oxygen carried? All of these questions are not really answered just by looking at ionic alone. And when we're looking at covalent compounds, following a few rules can really help us understand how the individual atoms will connect to one another in order to form covalent compounds. And so this slide here is really important. This is discussing how we end up making our compounds. And the idea is the same principle as ionic compounds, which wanted to gain and lose electrons to become more like a noble gas. Here, we still want that same number of electrons as a noble gas, which is usually 8. And we call this an octet. We want to form an octet, exactly 8 valence electrons in the outer shell, which is going to seem very similar to what we looked at with ionic compounds. But the difference here is that covalent compounds reach this goal by sharing electrons. And when they share electrons, both of the atoms that are sharing the electrons feel like it has a full outer shell. In other words, if I have atom A and atom B that each are sharing one of their electrons, both atoms A and B feel like they have 2 electrons since they both get a share of each electron. So covalent bonding, sharing of electrons, this is what we're looking at. And, when we're looking at covalent compounds, we want to really be very certain whether we're distinguishing an ionic or a covalent compound. And I think the easiest way to do this is to look for a metal, because metals really don't participate in covalent bonding all that much. They don't make covalent compounds, but they make a lot of ionic compounds, and we've seen a lot of these already. More specifically, we're looking for a cation, which 99% of the time is going to be a metal. So in these ionic compounds, the positively charged ion is a metal, whether it's Na, which is sodium, Ag, silver, Pb, lead, Fe, iron. These are making up ionic compounds. And if we look towards these covalent compound examples, we see that there are no metals. Metals tend not to form covalent compounds. These tend to be formed from a pair of non-metals. So this can give us a really good introduction on what should we be thinking about the chemistry and about the bonding. Is it ionic or covalent? And remember that they have very different physics, very different behavior. This is a picture of molecules, which is one that we may have seen before. This is CO2. If we have 3 individual CO2 molecules, note that we are showing covalent bonds between the 1 carbon and the 2 oxygens. That's what CO2 means. as this pair of lines between the central black atom and the outer red atoms. Each of these three CO2 molecules, though, is distinct from one another. It's like three pairs of socks, if you will. The socks have bonding that keeps them together, but the three pairs don't have anything that's holding them together that's quite the same as what is binding them into compounds, right? But a sodium chloride ionic compound structure is actually very different. We don't have one sodium and one chloride that are stuck together and then another pair with nothing in between. Ionic compounds are built on a negative and a positive charge canceling each other out, and they do this by forming large lattices where it's like a three-dimensional checkerboard, one cancels out the other. There's no real molecular individuality in the ionic compound structure, but there is in the covalent, and this is just to highlight how different these two bonding motifs are, and that we can see that right from the structure or even the name.